Hey class, hope you're doing well. So today we're going to talk about what's called the integral test. Before we jump into the integral test, let's just quickly remind ourselves what we've been talking about for series convergence and divergence tests so far. And then we're going to give a big overview or a big picture of what we're going to talk about for the integral test. Please check out the video. So far for our series convergence and divergence tests, we said we are handed some series from n equals 1 to infinity of some function a sub n. So again, this is some infinite sum, a1 plus a2 plus a3 and so on. And what we're trying to ask the question is whether or not this infinite sum converges, meaning this infinite sum equals some finite number. So the first test we introduced was called this test for divergence. And this test for divergence, as the name suggests, really kind of just tells us whether or not a series is divergent right from the start. So basically the test for divergence, we introduce a limit. We take a limit as n goes to infinity of our series function a sub n. And if this does not equal 0, the series is automatically divergent. So that's kind of the first part of this test. It can tell us whether or not a series is divergent right from the get-go. But the second part, and I want to caution us about this second part, is what happens when a series passes. So for example, if a series were to pass this divergence test or the test for divergence, it would just say, you know what? The limit of a sub n as n goes to infinity equals 0. And in this case, we get to do more work. We don't know whether or not this series is convergent or if this series is divergent at this point. We have to do more work to figure it out. It's sort of like just saying, you know what, the series passes the first test. So then we mosey on along to the next test that comes along. So from there, after the test for divergence, we introduced what's called the geometric series test. But again, as the name might suggest, this only works for geometric series. So a geometric series, just to remind ourselves, is a series from n equals 1 to infinity of some number a times another number raised to the n minus first power. And what was very nice about the geometric series test was if we have a series in this form, if it is indeed a geometric series, we can easily tell whether or not this series is convergent or divergent. So if we take the absolute value of r, the same r from our geometric series, if this is less than 1, the geometric series is convergent. But on the other hand, if when we took the absolute value of r, if this is greater than or equal to 1, the series is divergent. So geometric series test is basically when you identify what that r raised to the n minus first power is, the absolute value of r is going to tell you about whether or not this geometric series converges or diverges. So on that note, where we're going today is basically saying, you know what, we have a series that passes the test for divergence. And this series actually is not a geometric series that we're going to investigate today because geometric series have a particularly restricted form, as in, if a series is not in this form, it is not a geometric series. So we have to develop other tests now to figure out what a series does. So very quickly, the last thing I'll say about geometric series, though, is that if it converges, the unusual thing about geometric series is we know what it actually converges to. That is, we know what that sum of infinitely many numbers equals. So if we have the series from n equals 1 to infinity of ar to the n minus 1, our geometric series converges to a, which is the same a from our series, divided by 1 minus r, where r again is that same r from our geometric series form. And as we'll see as we continue along with infinite series, knowing what an infinite series actually equals if it's convergent is going to be a little unusual. So there's something special about geometric series here. So where we're going today is, like I said before, we're going to introduce what's called the integral test. And our motivation for introducing the integral test is basically we can apply it to a very broad range of series. So we're no longer restricted to just series in the geometric series form, or we're no longer restricting to say, hey, is this a harmonic series or isn't it? Or is this telescoping? The integral test is going to be our first test that we can apply to a broad range of series to decipher whether or not it converges or diverges. After that, we'll of course do some examples using the integral test. We're going to introduce then a special series called the p-series and prove when the p-series converges or diverges using the integral test. And I just want to write down this p-series. It's a series from n equals 1 to infinity of 1 over n. Again, n is our index, but that's being raised to the power p. And we're going to figure out using the integral test for what values of p will this p-series converge or diverge. And then lastly, we'll do a quick note about the integral test. And as a spoiler, this note is basically going to say, well, if the integral test guarantees that our series converges, we still aren't going to know what the series actually converges to. So that's what's on tap for today. Please check out the videos.